What's up, everybody? In the part 4 of this MPC playlist, now we are looking at a kind of a different type of problem. And here, this is the problem that we are going to discuss now. And first of all, we have two states, x1 and x2. Okay, but there is no u, right? There is no input term. And instead of that, I try to, find, hey, I am not going to find the input trajectory, right? Input time series, but rather, is it possible for me to basically determine a state feedback control law, right? Using MPC algorithm or using MPC and MPC type of ideas, right? Is it possible at least, right? And that's the question. And this is the type of question that people ask themselves, and that study field is called explicit MPC. Of course, this is not, this problem or this method is not explicit MPC at all. Explicit MPC is like some type of gain scheduling built into it, right? And yeah, it's not like that, but the idea is same. Hey, I don't want to create the input trajectory. I want to find the state feedback control law. Is it possible for me to do that by using MPC, right? Would MPC allow me to construct that state feedback control law? And of course, the answer is, if you ask me, I think based on the problems that are dealt with, I think it's not possible, right? However, let me say this, for like, this is the origin, right? This is the origin. Like, really small neighborhood. You at the end of solving this type of problem, you will get x1 and x2, and those x1 and x2 variables will be valid, right, for the small neighborhood of the, unlike the global stability type of things, small neighborhood of the origin, right? They will be able to make the system stable in the given and small neighborhood of the origin, basically, unlike the global stability, right? And first of all, if you look at the problem, and if we use this k1 and k2 values, we would get this. And this is a we have talked about this type of system before, right? This is global asymptotically stable, right? Okay. And the question is it possible for us to find these values using MPC? Can MPC find these values? And the answer is no, right? At least I couldn't find those values, right? However, let's try to solve this, right? Okay, let's attempt at least. All right, again, let's start by discretizing the nonlinear dynamics, okay, and continuous time dynamics. And here we have this, and we can see that we have 1, 2, 3, and 4 nonlinear terms, okay. And by using again Taylor expansion, right, around the given specific points, we can quote-unquote linearize those nonlinear terms, okay. All right, so here x1 is a trajectory, x2 is a trajectory. However, k1 and k2, those are just numbers, right? This is not trajectory. For example, this is a vector, this is a vector, but these are just numbers, right? And since this is nonlinear, right, and x1 appears in a nonlinear term, x2 appears in a nonlinear term, k1 and k2 also they appear, right? So we have x1 bar, x2 bar, k1 bar, and k2 bar, right? Okay, we have talked about this. This is like the part 4 of our MPC playlist. And okay, so mean this has two terms, right? Quadratic. Again, this is like a bilinear term, right? And and this has like three terms. But again, let's if you look at the part 2 of this playlist, you can see we also talk about the like this type of, if we have this nonlinear function, this this is our nonlinear function, right? And we also have x bar, y bar, and z bar, right? We would just I don't think I should write that, but I mean, since I started it, right? Okay, and x minus x bar, right? And plus I'm basically doing their series expansion. Okay, plus higher order terms, but we don't care about those, right? And so basically this is it. This is it, right? This is the Taylor approximation expansion of this function around this like point. Okay, and since we have, I mean, three terms, you can just write, hey, substitute k2 for x and and then substitute x1 of k for y and substitute x2 of k for z, right? And same goes for like x bar for k2 bar, right? Y bar for x1 of k bar, right? And z bar for x2 of k bar, right? This is the general idea. I mean, this the same idea. We are just using the same ideas over and over again, right? So let's go back to MATLAB, right? And try to look at this problem. And I am looking at this. Is it possible for me to delete some things? Wait a sec. Yeah. I mean, this line. Wait a sec. I don't know what to do. Wait a sec. This is a really long expression. I mean, yeah. Okay, I can do something like this, I guess. Okay, just delete this and okay. All right, let's change the screen. Okay, I think you are able to see that. At least I hope you are able to see that, right? Okay, I mean, all right, just start from sketch. Again, clear, right? And these are our dynamics, and we just discretize that, our continuous time dynamics. All right, again, n and t, like number of time steps and sampling period, right? And we use k1, we have k1 and k2, right? Okay, that's why it is like two variables. And also k1 bar and k2 bar, right? Again, if you recall, barred variables, we just define, or we just assign some things, right? Okay, all right. And by the way, since this is like a non-convex or nonlinear optimization problem, I think it's not surprising to find out the initial values that you pick, it very matters, right? Okay, just wanted to make that clear. Again, xvec, like x1 and x2 trajectories, and again their barred versions, x1 bar and x2 bar, right? And here the initial conditions, and also we want our stage to, this is a regression problem, we want our stage to go to, you know, 0 origin, right? Okay. And I use, instead of for, I use like cost function or infinite while loop, right? And the exiting condition is if we are not, you know, improving our cost value, right? And just break from that, out of that loop, right? Okay. So this is not different, right? We been using for loops, but now, yeah, this is like a sensible thing to do, right? And all right, again, we are, you know, putting our constraints in this object. Okay. And I'm looking at the screen, and I think you are able to see each and every one of the expressions. Okay. First of all, this is x1 dot expression. Okay. And it looks complicated. However, this is, let me check my notes, x2 square, right? This is x2 square. Instead of writing here x2 square, right? And here in the discrete domain, x2 square, we just written this, right? Why? We use Taylor expansion, right? Okay. And also, what was our second nonlinear term? X1 times x2. Yeah, I'm looking at my notes at the same time, right? And okay, this is it, right? This long expression is the expression that we substituted for x1 of k times x2 of k, right? Again, Taylor expansion, right? Okay. The third, what was the third nonlinear expression? K1. I'm looking at my notes, right? K1 times x2 of k, right? K1, right? And x2 of k. Again, this long expression, right? And the fourth expression and the final one is really long because it has three terms, right? K2 times x1 of k times x2 of k, right? Okay. And since it has like longer terms, its linearization is like really long, right? Really annoying. Okay, this long expression, right? Okay. Again, this is initial condition constraint, and this is initial condition, right? For x2, this is for x1, this is for x2, and this is our state magnitude conditions, right? Constraints, and we want our k values to be, you know, between minus 100 and 100, right? And by the way, we don't know anything about our, I mean, if we are being realistic about this, I mean, usually we don't know that. I mean, we will start from something like this, right? But we don't know this. Maybe k2 is like 200, right? Since this is like a nonlinear problem, we don't have any information. I mean, for this problem, this is like a toy problem, we will estimate something like this, right? I mean, we already know what our k1 and k2 values are, right? But for harder problems, I don't think there is something that allows us to, you know, write something like that condition. But again, we will start imposing that type of conditions to at least, hey, at least try to solve this. If it's not, okay, let's change the constraints, right? This is like the general, I guess, decision process, right? Again, solver, and this is our objective function. Again, solve this optimization problem, and this is the cost, and in the previous it says previous cost, and this is this current iteration, right? And the cost of the previous iteration, right, is stored in this variable, right? Okay, because we are just keeping current cost and also previous cost. Why? Because we are looking at them, and if we are asking ourselves if we are improving on that, right? If we are not improving, okay, let's break out of the loop and end the program. Okay, all right, and write down the results. All right, and again x bar, just solve for x and store it, and x bar and iteration, right? This is like alternation technique. Okay, and yeah, I just written something like this, right, thinking it would help a bit, and it takes, yeah, again, sometimes, right? So I think you are able to see that, and now I am going to do something like this, so you would be able to see that, right? Okay, let's run it. And how many iterations? I'm looking at my notes. It's gonna take some time. I mean, okay, but I didn't want to pause it because I want kind of you to see this, because it's not like it solves like instantly for every problem, right? And yeah, I mean, each iteration, each step, right, it solves fast, right? But the convergence of x bar trajectories, they take some time. Okay, I'm thinking right now if I pause it. Wait a sec. Oh, it didn't solve that. Oh, so I think I should pause it 1 sec. Okay, now it solves that. I mean, since we are initiating, x bar and also k bar values. No, this is not random, but since we are initiating them, right, and randomly, I think better thing for us to do is to initiate k bar values using random, I mean arbitrarily, right? And yeah, it solved that, right? And let's plot it. We don't have inputs, by the way. Input, we just have k1 and k2, right? Okay, so we don't have u of t, but x here, red line indicates, maybe let's zoom it a little bit, right? Yeah, here we can see this red line is for x1, and this black line is for x2, right? And let's look at our k1 and k2. Yeah, they are here. I mean, we wanted to find x1 k1 as -2, right, and k2 as -1, right, and here -2 and -1, and no, it didn't find that. However, if we use SOS programming techniques, and and also for, I guess, and also like analyze these variables and to see, I mean, what's the neighborhood that these values are able to stabilize the system, right? Maybe it's a ball like 0.1, right, and with radius 0.1, or maybe it's larger than that, right? And whenever you have that type of k1 and k2 and maybe more like coefficients, and these coefficients basically your state feedback control law, right? And then you can analyze those variables to see if they are, or what is the radius that these variables are able to stabilize your system. Okay, basically. Okay, and based on the problems that I dealt with, I don't think you would be, I mean, even for the simplest problems, you would be able to, find a state feedback control law that would, stabilize the system in a global sense, right? But for some problems, I mean, local stability, right? Local asymptotical stability is something that you can sometimes, right? Again, not always, but sometimes you can get. Yes, sometimes you can solve all those type of problems if global asymptotic is not that important for you, but only like local stability is the thing that you are aiming for. Yeah, I think this type of ideas you can use that, right? Okay, so yeah, this is the interesting topic, right? And hopefully in the future I will learn more about. And by the way, again, uh, remark, this is not explicit MPC, is not this to my knowledge, right? Hopefully in the future I will but learn about explicit MPC because it's an interesting topic, right? All right, so that's it for today, and thanks for watching.